So good evening students, continuing with the problems of unit number 4. Let us start with problem number 4. The problem number 4 is the electric field intensity of a uniform plane in air has an amplitude of 800 volt per meter in x direction. If the wave is propagated in z direction and has a wavelength of 0.6 meter, find frequency, time, beta, that is phase constant, and amplitude of h vector and direction of h vector. So in the problem the given data is Ex value is mentioned, that is 800 volt per meter, and the lambda value is 0.6 meter. So to calculate first frequency, the formula for frequency is V equal to lambda into F. To calculate the frequency F equal to V by lambda, the value of V, that is velocity of propagation, is 3 into 10 raised to power 8 divided by 0.6. 0.6 is the value of lambda. So F equal to 500 megahertz. Then time T equal to 1 by F. We have calculated the frequency F. So 500 megahertz. So 500 into 10 raised to power minus 6. So T equal to 2 into 10 raised to power minus 9 second, equal to, that is nothing but 10 raised to power minus 9. So 2 nanosecond. Then C is to calculate the value of beta, that is phase constant. The formula is lambda equal to 2 pi by beta. So beta will be equal to 2 pi by lambda. So 2 pi by 0.6. That is the value of phase constant beta is 10.479 radian per meter. And the last is amplitude of h vector. So amplitude of h vector formula is E equal to n into h vector. So h vector equal to E divided by n. The value of E is given, that is 800 volt per meter, divided by the constant value of intrinsic impedance is 377, which is equal to 2.1220 ampere per meter. Now also it is asking in the problem the direction of h vector. So direction of magnitude of field is with respect to h vector, that is h equal to one is given as has a wavelength direction, so AW multiplied by the AZ, wave is propagated in the AZ direction. So the wavelength is AW, and it is given that the uniform plane wave in the amplitude of 800 volt meter x direction. So AE is x. So AW is AZ and AE is x. So the cross product of AZ multiplied by AX is AY. So therefore the direction of magnitude of field towards the H vector is AY. So this is about problem number 4. Let us take another example. That is problem number 5. Problem number 5 is a 9.4 gigahertz. A 9.4 gigahertz uniform plane wave is propagating in epsilon r equal to 2.56 if the amplitude of magnetic field intensity is 7 milliampere per meter and material is assumed to be lossless. find number A velocity, number B lambda, number C beta, then D is eta, E is amplitude of electric field intensity, amplitude of electric field intensity. So solution of this problem is, the given data is F equal to 9.4 into 10 raised to power 6 hertz. It is given that 9.4 gigahertz frequency, and the value of epsilon r is 2.56 and h is 7 milliampere meter. Now first case, to find the velocity. So velocity formula is v equal to 1 over under root of mu epsilon. So as we know that for free space mu is mu 0 mu r, and for epsilon is epsilon 0 epsilon r for the free space. Here again, as the material is lossless, assume that mu r equal to 1. So 1 upon under root of the value of mu 0 is 4 pi into 10 raised to power minus 7 multiplied by 1 is mu r multiplied by epsilon 0, the value is 8.854 into 10 raised to power minus 12 multiplied by epsilon r. Epsilon r is given, that is 2.56. So the velocity of propagation v equal to 1.8735 into 10 raised to power 8, that is in meter per second. Now second is to find the wavelength. So P, we find wavelength, that is lambda. Wavelength. So the formula to find the lambda, we have velocity. So V equal to lambda into F. So lambda which will be equal to V divided by F. Velocity we have just calculated. So it is 1.8735 into 10 raised to power 8 divided by frequency it is given, that is 9.4 into 10 raised to power gigahertz. Giga is 9, 10 raised to power 9. So the value of lambda becomes 0.0198 meter. Then C, to calculate beta, to find the phase constant, beta equal to omega under root of mu epsilon. So omega is twice pi f under root of mu 0 mu r epsilon 0 epsilon r. So it is 2 pi multiplied by frequency is again 9 into 10 raised to power 6, or you can put the value of here frequency which is given, then mu 0 is the value of mu 0 is 4 pi into 10 raised to power minus 7. Here mu r is 1, epsilon 0 is again 8.854 into 10 raised to power minus 12, and epsilon r is given, that is 2.56. So you will get the value of beta, that is 315.211 radian per second. Now to find the intrinsic impedance. So to find the intrinsic impedance, that is E. Intrinsic impedance. So formula is theta equal to under root of mu divided by epsilon. So again mu is mu 0 mu r divided by epsilon 0 epsilon r. So mu 0 is 4 pi into 10 raised to power minus 7 multiplied by mu r is 1 divided by epsilon 0 is 8.854 into 10 raised to power minus 12 multiplied by epsilon r is given, that is 2.56. So the intrinsic impedance theta will be equal to 235.4589 ohm. And also it is asking amplitude of electric field intensity, that is E. The amplitude of electric field intensity is, again formula is E equal to theta and pH. So E will be equal to the value of N theta is 235.4589 multiplied by pH is given, that is 7 milliampere. So 7 into 10 raised to power minus 3. So E will be equal to 1.6482 volt per meter. So this is the problem number 5. Now similarly you can check in the notes. I have solved the problem number 6. The sixth problem number 6 is already, it is in the same process or same steps you can use and find the solution. Now I am going to the another topic. So the next topic is conductor as a dielectric. Conductor as dielectric. Now Maxwell's first equation in phasor form for a general conducting medium is given by curl cross Hs equal to sigma plus j omega epsilon into Es vector. So sigma into Es multiplication, taking multiplication plus j omega epsilon into Es. So this sigma into Es, it is nothing but Jc, and j omega epsilon into Es, it is nothing but Jd, where sigma into Es is the amplitude of conduction current. This is called as amplitude of conduction current, and Jd is called as amplitude of displacement current density, and this Jd is amplitude of displacement current density. This is the meaning of Jc and Jd. Now the ratio of conduction current density, and the displacement current density is used to define the medium of conducting or dielectric or conductor. So by taking the ratio of Jc divided by Jd, which will be equal to sigma, the value of Jc is sigma into Es divided by the value of Jd is j omega epsilon into Es. So this Es get cancelled. So the value will be sigma upon j omega epsilon. Now here if you note that what is the value of j? J is nothing but the imaginary component and this is the real component. So we can't take this the value of j. Since this is nothing but the imaginary component. So the condition for perfect dielectric medium is dielectric medium. So Jc is less than Jd is the first condition. So Jc divided by Jd is less than 1. That is nothing but the value of Jc divided by Jd is sigma upon omega epsilon is less than 1. Similarly, another condition, that is for perfect conducting medium. Condition for perfect conducting medium. So the condition is Jc is greater than Jd. So Jc is greater than Jd is greater than 1. So it is again sigma upon omega epsilon is greater than 1. And if you take the example of good dielectrics, for good dielectrics, Jc is very less than Jd. So therefore Jc divided by Jd is very less than 1. So sigma upon omega epsilon is very less than 1. And the condition for good conductor is Jc is very greater than Jd. Similarly, Jc divided by Jd is very greater than 1, and therefore sigma upon omega epsilon is very greater than 1. So this is about the conductor as a dielectric. Now next topic is loss tangent. What do you mean by loss tangent? Because sometimes in the paper asking the definition of what do you mean by conductor as a dielectric and what do you mean by loss tangent. Loss tangent. So the loss tangent is defined as the tan of phase angle. Loss tangent is defined as tan that is tangent of phase angle, tan of phase angle between the conduction current and displacement current. Between the conduction current and displacement current. Just now we have seen the conduction current and displacement current, that is denoted by Jc and Jd, and it is denoted by del. This loss tangent is also defined as the ratio of conduction current density and the displacement current density. So loss tangent is also defined as loss tangent, which is denoted by del, and sometimes it is, we can say, tan of angle phi, which is the ratio of conduction current density Jc divided by displacement current density Jd. The value of Jc and Jd, that is nothing but sigma upon omega epsilon. So therefore the loss tangent, which is denoted by del, equal to, equation is tan phi equal to sigma upon omega epsilon. So this is about loss tangent. I have also solved the derivation for wave propagation in good conducting medium in the notes, but that is not important for the problem point of view. Also, the derivation point of view. So that's why I am stopping this topic here only. Thank you for the listening.